Okay, Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. So, this week we are already in week 5. So we are going to continue our online course, chapter 3. So I will share the tab with you. Okay, I hope you can see this. Okay, so now we are going to see, I'm going to introduce to you chapter 3. We have seen chapter 1, the introduction to air breathing engine, and the second chapter, introduction to some of the performance parameters in order to evaluate air breathing engine performance, which is the most important ones are the thrust force, the propulsive efficiency, and the TSFC, which is thrust specific fuel consumption, or just SFC, specific fuel consumption. Okay, those are the performance parameters. Okay, so now chapter 3, we are still going to look into turbojet and turbofan engine, but more into detail of this engine, the process, etc. Okay, so this chapter is going to be about turbojet and turbofan engine. Okay, so introduction again. Okay, I have introduced to you before the turbojet engine. So, but in this chapter, I'm going to go into more detail. Okay, inshallah. So, okay, first, turbojet engine. Okay, the most basic engine, the first one. Okay, so this is example of single spool turbojet engine. Okay, so as you can see here, we have the inlet intake where the air will go into we enter the engine, okay, the turbojet engine, and then we have compressor, okay, compressor after the inlet intake, then the air, the fluid will be compressed and goes into the combustion chamber where the fluid will mix with the fuel, and the combustion process will occur here in the combustion chamber or in the burner. We call it burner heater. And then the temperature will heat up, okay, until at the inlet of the turbine. And the inlet of the turbine usually will be the highest temperature achieved by the air, by the fluid inside the engine. Okay, the highest temperature achieved is at the turbine inlet temperature. Okay, so we have the turbine where the air will be expand, okay, and the temperature also will decrease a bit. And then nozzle, okay, nozzle or exhaust, okay, exhaust nozzle where the air will be accelerated, okay, the velocity will increase to a high speed velocity, okay, and at the end it will exit the engine. Okay, so this is the basic turbojet engine, which is invented by Sir Frank Little and Dr. Hans von Ohen. Okay, so turbojet engine is a very, very powerful engine, okay. So this is a single spool. Single spool means one shaft. Okay, we only have one compressor and one turbine. Okay, at each end, at either ends of the shaft. Okay, compressor and turbine. One compressor, one turbine. So that is called one shaft or single spool turbojet engine. Okay, next, two spool. Okay, two spool turbojet engine here. So what is the difference between two spool and single spool turbojet engine? So here you can see we have more components. Okay, we have more components. The extra components here we have LP compressor, HP compressor, HP turbine, LP turbine. So what does it mean? Okay, LP means low pressure. So low pressure compressor, and HP is the high pressure compressor. So HP turbine, high pressure turbine, and last one LP turbine, low pressure turbine. So for two spool turbojet engine, the extra component is the low and high pressure of the compressor and turbine. Okay, so the turbine and compressor are divided into low pressure and high pressure. Okay, So we have two spool, mean we have two shafts. So we have two compressors and turbines. Okay. So the first set of compressor is called LPC, or low pressure compressor, which is driven by the low pressure turbine. Okay. Together, okay, the shaft are noted as low pressure spool. So the low pressure spool consists of the low pressure compressor and low pressure turbine. Okay, so that is the low pressure spool. Okay, as you have learned in aerothermodynamic, the function of a turbine is to drive, okay, to drive the compressor. The turbine will produce power output, where the power will be used to drive back the compressor and repeat the cycle, right? In thermodynamic, you have learned that. So for each spool, the low pressure turbine or the high pressure turbine, the power produced will be used, some of them, not all, okay, some of them will be used to run the compressor. Okay, so to run low pressure turbine is to run the low pressure compressor, and the high pressure turbine is to run the high pressure compressor. Okay. So for the high pressure, okay, the HPC is driven by HPT, high pressure turbine, and both constitute the modus of the high pressure spool. Okay, so we have low pressure spool and high pressure spool. Okay, that is why we call it as two spool turbojet engine. Okay, so what are the interests? Okay, why? Okay, so multiple spools are used in the engine. So multiple, because some of the engine even they have three spools. Okay, so they have low, medium, and high spools. Okay, so there are multiple spools are used in the engine, so that each one may rotate at a different speed for optimum efficiency. In order to have a more optimum efficiency, so if you have a two spool or three spool turbojet engine, so each of these spool can run independently at different speed. So we can optimize the efficiency of the engine. Okay, that is the purpose. Okay. Okay, but of course, having two or three spool or multiple spool engine, of course, it will give more weight. Okay, more weight, increased cost. Yeah. But at the same time, if you want to optimize the efficiency, then we will choose multiple spool. Okay, so the main point in this chapter is to understand the process, okay, the process inside the engine, the thermodynamic process, okay, the cycle, okay. So the thermodynamic cycle, okay, this is the schematic diagram of a turbojet engine, okay, single spool turbojet engine, the schematic diagram here. So we have the first location A is the point of ambient, okay, at the intake before entering the engine. A is still outside the engine at the ambient environment air. Okay, and then we have diffuser 1 to 2. So remember, diffuser is the opposite of the nozzle. Okay, if nozzle is used to accelerate to high speed velocity, diffuser is the opposite. It is to decelerate. Okay, decelerate the air, because the air intake here from the environment, from the ambient, is at a high speed. Okay, so we will want to decelerate. Okay, decelerate. If possible, in ideal case, we want to decelerate adiabatically. Okay, to stop isentropically. Okay, adiabatic reversible. Okay, so we want to decelerate the velocity of the air, so the velocity will decrease, the kinetic energy will decrease here. Okay, and then we have compressor to compress. Okay, to compress, so pressure increase, temperature increase. Okay, so and then we have burner. Okay, burner or combustion chamber, where the in ideal case, we suppose that the pressure is constant in the burner, but in the real case, normally we have a slight pressure loss within during the combustion process. Okay, otherwise the temperature, of course, will increase because we heat up. Okay, we mix the air the oxygen, air with the fuel. So we will increase the temperature obviously. And then turbine, expansion, okay, reduce pressure and reduce temperature. And okay, afterburner. Okay, afterburner is an extra, some turbojet engine have has extra component which is afterburner. So means that it has two burners. Okay, afterburners means that we burn it. The combustion process will happen one more time. Okay, so we have two combustion process, burner and afterburner. If the engine has a the afterburner. Okay, so why the function is that we want to increase more the temperature so that we can increase more the velocity, the kinetic energy at the exit nozzle. Okay, to increase the velocity, to, of course, to increase thrust power. Okay, but we need more fuel. If we add extra afterburner, then we need more fuel. Okay, to increase the temperature and then increase the velocity, kinetic energy. Okay, so this is the detail of the thermodynamic analysis. This one you have to absolutely understand and memorize. Okay, what I mean by memorize is that you have to be clear. Okay, be not memorize word by word, but you have to as a propulsion engineer, okay, aerospace engineer, engine, you have to understand clearly this one. Okay. So the process, the thermodynamic analysis, okay, so from ambient to intake at point one of the diffuser, at the diffuser intake, so what happens is that from far upstream, okay, from the environment, the velocity of the air, okay, is the flight velocity, okay? Okay, so we consider here the velocity of the air is the same as the flight, is what we call the flight velocity, okay? So the air is brought to the intake, at the diffuser, okay, usually with some acceleration or deceleration, okay, so we decelerate obviously, okay, and then from 1 to 2 in the diffuser, okay, the air velocity is further decrease, okay, decelerate, further decrease, as okay, in the diffuser the function is to decrease, remember, opposite of the nozzle. The function is opposite of the nozzle, decrease to decelerate, okay, velocity, as the air is carried to the compressor inlet through the inlet diffuser and ducting system. Okay, so before entering the compressor, the air velocity will be decreased first. Okay, we will decrease the air in the diffuser. Okay, that is the function of the diffuser. Okay, and then next 2 to 3 compressor, the air is compressed in a dynamic compressor. Okay, and then of course other than compress, pressure increase, the pressure also will increase in the compressor. 3 to 4, the air is heated by the mixing and burning of fuel in the air. So the fuel and the oxygen in the air will mix up and the combustion process will occur here and the temperature will heat up. 4 to 5, the air is expanded through a turbine to obtain power to drive the compressor. Okay, like I've said just now. So the air will expand, okay, in the turbine, expansion, pressure decrease and temperature decrease, okay, and then will produce power. If you remember the video from the YouTube that we have seen during our first week of introduction, okay, why, how come in the turbine, okay, when we expand, we are able to produce power, okay, we are able to increase the energy to kinetic energy. Remember? Okay, so here at the exit of the burner or combustion chamber, the temperature is high, right? Okay, so due to the conservation of energy, okay, conservation of energy, so the pressure energy, okay, the pressure energy, the pressure and the temperature at the inlet of the turbine or at the exit of the burner, temperature is very high. Okay, so the main types of energy here is the thermal energy. Okay, so the air is full with thermal energy and pressure energy, and this pressure energy will change, okay, will change to kinetic energy. Okay. So when pressure energy decrease in the turbine, kinetic energy will increase. Okay, so due to the conservation principle of the conservation of energy, pressure energy decrease, kinetic energy increase. So that's why at the nozzle, the velocity is high, kinetic energy increase. Okay, we convert the pressure energy, conservation of energy, pressure energy to kinetic energy. Okay. So the power to drive the compressor. So the power produced will go back, some of them, not all, will go back, will be used to drive the compressor, just like the power plant. Okay. 5 to 6. Okay. The air may or may not be further heated. Okay. Depends if we have or not the extra afterburner. Okay. By the addition and burning of more fuel in an afterburner. Okay, 6 to 7, the air is accelerated and exhausted through the exhaust nozzle. Okay, so high speed gas flow here. Okay, so this is the ideal case. So in this propulsion course, I will introduce to you the ideal case. Okay, only the ideal case. Later on, like I've said, there's another course about the engine, which is air breathing engine, which is an elective course during your final year. You can take that one. Okay, so in that air breathing engine, you will be introduced to a real case of turbojet and turbofan engine. Okay, so in propulsion, we're only going to see ideal case. So it's easier because otherwise for real case, there's more parameters that you have to be alert. Okay. Okay, so the thermodynamic path of the fluid with the turbojet may be conveniently shown on an enthalpy entropy or temperature entropy diagram. Okay, so we use in order to further describe the thermodynamic analysis, we use the enthalpy entropy or temperature entropy diagram. Okay, you know this by now, right? We have learned this in aerothermodynamics. So the usual one, you will use temperature entropy diagram, TS diagram, okay, to describe the process. To gain an understanding of the overall process, it is useful at first to study a highly simplified model. Okay, so we try to use ideal case first. Okay, for this reason, let us assume that all components except the burners are reversible and adiabatic. So we assume in ideal case, we assume that all components, the diffuser, the compressor, the turbine, all are reversible and adiabatic, ideal. Which is isentropic. Okay, reversible adiabatic means isentropic. That the burners may be replaced by a simple frictionless heaters and that the velocity is 2 to 6, the location just now, 2 to 6, okay, are negligible. Okay, so all components are considered as isentropic except the burner or the combustion chamber. We use a simple frictionless heater. So we still assume that the burner is frictionless. There's no friction. Okay, and that the velocities 2 to 6 are negligible. Okay, so we assume there are no kinetic energy produced or lost between 2 to 6. Okay, so kinetic energy, we assume the kinetic energy only occur at diffuser and nozzle. Otherwise, between compressor until number 6 here, we assume that the kinetic energy is very small, that we can neglect. Okay, the TS diagram is shown for non-afterburning and afterburning engine, assuming the working fluid to be a perfect gas. So we assume, in ideal case, we assume that the fluid, the air, is a ideal gas. So we can apply the ideal gas law. Okay, so this is the TS diagram, temperature entropy diagram of an ideal turbojet engine. Okay, so we have air intake and then straightly to number 2. Okay, here we use number 2. Okay, at the diffuser, okay, air intake diffuser, and then just a slightly different. So actually, in ideal case, the ambient and the inlet of the diffuser is practically the same point. Okay, the same, have the practically generally the same property. So that's why it is as if at the same point, temperature, pressure is the same. Okay, we assume that inlet the diffuser, the properties, the characteristic of the air at the inlet of the diffuser is the same as the ambient. Okay, so T2 to T3 is the 2 to 3 we have the compressor. Okay, 3 to 4 just now the burners or the combustion chamber. 4 to 5 is the turbine expansion. And then if we have the afterburner operating, then 5 will go to 6A. Otherwise, the point 5 and 6 is the same. If we don't have afterburner, then the 5 and 6 is the same. So 6 go to 7 in the exit nozzle. If we have afterburner, so 6A to 7A. Okay, exit of the nozzle if we have afterburner. A is afterburner. Okay, so remember I said just now, if we don't have afterburner, then the highest temperature achieved is at 4, T total 4, which is the turbine inlet temperature. Otherwise, if we have afterburner operating, then the highest temperature achieved, maximum temperature, is the temperature exiting the afterburner before going into nozzle, which is T6A. Okay, so in the ideal case, the pressure rise from A to 1 and still more from 1 to 2. Okay, so 1 is the inlet diffuser, so we assume is kind of at the same point. Okay, but the pressure still rise as the air is decelerated relative to the engine. Okay, since the velocity at 2 is assumed 0 and this deceleration is isentropic, ideal. Okay, P2 is the stagnation pressure for states A, 1 and 2. Also, T2 is the stagnation temperature for these states. Okay. You will see. Okay. So actually, this is we have equations. Okay. General equation for this. We will see these equations next week, inshallah. Okay, during the tutorial exercise. Okay. So there are some equations that need to be used. Okay, to define the process. And then the power consumed in compression from 2 to 3 must be supplied through the turbine expansion from 4 to 5. Okay, turbine. Okay, so this is the same as the process I have explained just now, except that here we have to include the equation. Okay, from the shape of the constant pressure curves, we can see that T6A, T7A is greater than T5, T7. Okay. Okay, so we see here, okay, 6A, T6A, the difference between T6A and T7A is higher than the difference between T5 and T7, right? Okay, that's what you mean. And hence the exhaust velocity will be greater in the afterburning case. So that's why we add the function of the afterburner, okay, because the difference of the temperature will be higher. So we expect to produce more kinetic energy, more high velocity, high speed gas by adding the afterburner. Okay, here by looking at this temperature, the difference of the temperature. The higher the difference of the temperature, the more kinetic energy that we expect to produce. Okay, so this is due to absence of highly stressed material in the afterburner. Okay, so T, like I've said just now, if we have afterburner, then the point 6A is the maximum temperature that we have, which is higher than the turbine. TIT is turbine inlet temperature, which is the point 4 just now. Okay, so if we have afterburner operating, so the the temperature at the exit of the afterburner will be the highest instead of T4, the turbine inlet temperature. So advantage of afterburner, the jet speed will increase more. Okay, that is the first interest. The thrust of the engine increase without adding much weight. Okay, we are able to increase the thrust force. Disadvantage, of course, we use a lot of fuel. Okay, because we have to burn the air one more time. So we use fuel, extra fuel, okay? Okay. Okay, next is the turbofan engine. Okay, so turbofan engine is kind of the same as the turbojet engine, except that we have the fan, of course. That's why it is called turbofan. So we have fan, okay, fan unit and compressor section, combustion chamber and turbine section. Okay, so the advantage of turbofan engine is that, okay, why we add turbofan engine? I think I have mentioned this in the previous chapters. The fan is not as large as the propeller, okay, because we want to compare with the turboprop. Okay, fan is not as large as the propeller, but it is able to higher aircraft velocity before vibration occurs. Okay, so uh, okay, so the fan is not as large as the propeller, so it is able uh, to uh, to have, okay, to increase velocity before vibration occurs, because normally if the fan or the propeller is large, okay, so it will affect, it will produce vibration, okay. So so that's why by using fan instead of the propeller, uh, we are able to have a high velocity of the aircraft before vibrations start to occur, okay. The fan is more stable. Okay, vibration are less apparent and do not disrupt the airflow. So again, because of the vibration, the advantage is less vibrated. The fan is encased in a duct. Okay, like I've mentioned before, we have like a bypass duct. Okay, so the fan is inside there. Okay, so the aerodynamics of the airflow is better controlled, so we can control the flow. Okay, the turbulent flow. Okay, so we are able to achieve greater efficiency. Okay, this is not the main objective of this propulsion, but if we learn aerodynamic or control subject, okay, we know that by having the encased duct, okay, the aerodynamic of the airflow is better controlled, thus we can achieve better efficiency. Okay, the smaller fan is more efficient, it's in air at greater rate, thus producing greater thrust. Okay, so it is more beneficial to use a smaller fan. And turbofan also much more fuel efficient design than the turbojet. Okay, because turbojet use more fuel. Okay, turbofan it use less fuel, but it still can produce higher thrust. Okay, so this is the single spool mixed flow turbofan engine. So turbofan have two types of exhaust. Okay, mixed and separate exhaust. So this is mixed exhaust. Okay, mixed means that the air, okay, from the bypass duct, okay, and the core engine means the hot and cold air will mix, okay, will mix together before exiting the nozzle. So that's what it means by mixed flow. Okay, the cold air from the bypass duct and the hot air from the core engine will mix together, will be mixing together before exiting the nozzle exhaust or exhaust nozzle. Okay, so at nozzle exit, fluid flow at primary and secondary nozzle are mixed. Okay, primary, secondary, the hot and cold. Okay, remarks. Okay. Okay, so remarks, increasing the BPR. BPR is the bypass ratio. Okay, improves the SFC at the expense of significant reduction in specific thrust. Okay, so if we increase the BPR bypass ratio, so if the bypass ratio is higher, means that we use a lot more air intake. Okay, the air in the bypass duct is higher. Okay, means the cold air is a lot more. Okay, we are able to improve the thrust specific fuel consumption. Means that by using a higher bypass ratio, higher air at the bypass duct, we are able to produce thrust, the same amount of thrust, but with less fuel. Okay, improve TSFC. Less fuel but with the same thrust produced. Okay, I repeat, if we increase the bypass ratio, means that we increase the air intake in the bypass duct, we are able to produce the same amount of thrust but with less fuel. Okay, improve TSFC means that the TSFC is lower, which is good. Okay, our objective is to have a lower TSFC. A lower TSFC means that lower, less fuel use in order to produce the same amount of thrust. Okay, so at the expense of significant reduction in specific thrust. Okay, so because the specific thrust is thrust over the mass flow rate of the air intake. So if the mass flow rate of the air higher, so specific thrust will be lower. The optimum fan pressure ratio increase with increase of turbine inlet temperature. There's a lot of short form here. Okay. The maximum thrust and specific thrust occur at a definite overall pressure ratio. Okay, these are just remarks. Okay, I think the first one is more important. Okay, application. Okay, the application of the turbofan engine, long range subsonic transport. Okay, for long range subsonic transport. Okay, subsonic Mach number below than 1. The TFC is of major importance. Okay. So for long range journey, our main objective is to have less TSFC. Okay, our main focus is TSFC. Okay, for long range. Okay, so it depends actually in this in propulsion engine. The parameters that we want to optimize depends on our objective of the mission. Our mission objective means, is it a long range journey or short range journey? Is it for military? Is it for civil aircraft? So it depends. So that's why we don't have one exact solution for optimum performance. So it depends on your mission. What are your missions? Okay, so for long range subsonic transport, long range, our focus is TSFC. Okay, we want for long range, long journey, we want to to save fuel as much as possible. So that's why TSFC is of major importance. So this is achieved, like I've said just now, through BPR in the range of 4 to 6. Okay, bypass ratio around 4 to 6, and high overall pressure ratio and low turbine inlet temperature. Okay, so if we have higher bypass ratio around 4 to 6, overall pressure ratio high, and low turbine inlet temperature, then we are able to have optimized TFFC. Okay. Otherwise, second objective is military aircraft. Okay, for military aircraft, supersonic capabilities as well as good subsonic fuel consumption are the major objective. Okay, so for military aircraft, the important is to have a high speed velocity. Okay, military. So for military aircraft, if we use turbofan engine, we will use rather a smaller BPR, bypass ratio, around 0.5 to 1. Okay, so we have small frontal area of the fan, and adding an afterburner. So, and we add afterburner to increase the velocity for military aircraft. For short commercial aircraft, short civil aircraft, short range, BPR is rather small, is similar to the long range subsonic transport. Okay, so around 4 to 6 or so, which also minimize noise. Okay, this also can minimize the noise. So BPR is quite the same. Okay, so that's it. The description, okay, of the turbofan and turbojet engine. Okay, so at least the objective of this, the outcome from this chapter is for you to understand the detailed process, the thermodynamic process of the turbojet and turbofan engine. Okay, so from 1 to 2, 2 to 3, like the power plant in aerothermodynamic that you have learned, what happens to 1 to 3 from location 2 to 3, 2 to 3, what happened, 4 to 5, what happened, whether the temperature increase, pressure increase or what, okay? That is the important thing that you have to know. From there, then you will understand how to evaluate the performance of the turbofan and turbojet engine, okay? So of course, in order to analyze, to evaluate the performance of turbojet and turbofan engine, we have equation for each, like power plant in aerothermodynamics. So you have equation for each step. Means from 1 to 2, what is the equation? From 2 to 3, what is the equation? 3 to 4, what is the equation? Equation use, formula use, right? Until at the end, you have the efficiency, the thrust produced, the power that you want to evaluate, right? So the same in the turbofan and turbojet engine, the equation that will be used. Okay, but I will introduce those equation next week during the tutorial, because from there you can look at the equation and then simply apply it. Okay. Okay, I think that's all from me for now. Okay, hope you understand this chapter. Okay, if you have time, try to, you can also start to look at the equation of the process, the thermodynamic analysis process. Okay, so like I have mentioned, we assume ideal case, so obviously we will apply the ideal gas equation. Okay, just like in the power plant. Okay, except that here we remember we use high speed gas flow, so we have to include Mach number. Okay, from the Mach number, how do we derive the equation of turbine pressure, etc. Okay, that's all from me. Thank you very much. Hope you understand this online course. Thank you.